Welcome to our deep dive into fraction multiplication. Let's start with a foundational concept. In mathematics, the word of is a powerful signal. It almost always translates to multiplication. When we look at this rice problem asking for 1/5 of 5 kilograms, we aren't just doing a random calculation. We are finding a specific portion of a whole quantity. Think of it as taking that 5 kilos and dividing it into 5 equal piles, then selecting just one. This conceptual understanding that of means multiplication is the key that unlocks all the word problems we'll face today. Now, let's look at example 1 with boxes of blueberries. Each box represents a unit fraction, 1.8 of a kilogram. When we have 3 boxes, we are effectively adding 1.8 to itself 3 times. But as we know, repeated addition is the very definition of multiplication. The bar model here is crucial. It shows a single kilogram divided into 8 equal parts. By stacking 3 of these 1/8 kilo boxes together, we can visually see that they occupy 3 out of those 8 original slots. This visualization bridges the gap between a physical object and an abstract numerical expression. Let's break down the actual calculation mechanics. When you multiply a fraction like 1/8 by a whole number like 3, it's helpful to imagine the 3 as a fraction itself, 3 over 1. Then the rule is simple. Multiply the tops and multiply the bottoms. 1 times 3 is 3, and 8 times 1 is 8. This is why the denominator stays as 8. You haven't changed the size of the pieces. You've only changed how many pieces you have. We started with one piece of size 1/8. And now we have 3 pieces of that same size, giving us 3.8 of a kilogram. Example 2 steps up the difficulty by introducing mixed numbers and unit prices. We have lemons at $4 and $7.10 each. To find the total for 6 lemons, we use 6 as our multiplier. Look closely at the analysis diagram. It represents the total cost as 6 identical segments. Conceptually, we are multiplying a whole number and a fraction part simultaneously. Before we can easily solve this, we'll need to transform that mixed number into an improper fraction, a crucial step we'll see in our next example. Always remember, in word problems, identify your rate, the price per lemon, and your quantity, the 6 lemons. In example 3, we see Mom buying 3 1/2 kilo of carrots at $9 and $15 per kilo. This is a real-world scenario where visualization is your best friend. The bar model shows 3 full 1 kilos blocks plus a half block. Each of those full blocks costs $9 and $15. To solve this, we don't just multiply the whole numbers and then the fractions separately. That's a common mistake. Instead, we convert both to improper fractions. 3 and 1/2 becomes 7/2, and 9 and 1/5 becomes 46/5. Multiplying these together ensures every part of the weight is multiplied by every part of the price. Example 4 shows how to find a fraction of a large whole number, 4/9 of 540 milliliter. Think of the 540 milliliter as a single container. The fraction 4/9 tells us 2 things. First, that we should imagine this container divided into 9 equal sections. Second, that we are only interested in 4 of those sections. In your mind, you should be asking, if 9 sections equal 540, what does 1 section equal? That's 540 divided by 9. Once you know that 1 section is 60 milliliter, you simply multiply by 4 to get your final answer. This 2-step logic, divide by the bottom, multiply by the top, is a foolproof strategy. Finally, let's master the art of simplification. As shown on this slide, we set up 540 times 4 over 9. We could multiply 540 by 4 first, but that gives us a very large number to manage. Instead, look at the 540 and the 9. Since 54 divided by 9 is 6, we know 540 divided by 9 is 60. We cross out the 9 and the 540, replacing them with 1 and 60. Now, the problem is just 60 times 4, which is 240. This is called cross reduction, and it's the professional way to solve fraction problems. It keeps your numbers small and your accuracy high. Great job today. We'll continue this deep dive in video 2. Welcome to our enhanced guide for video 2. We start with a consolidation exercise on slide 14. We have 3 to 4 of a liter of juice in 1 carton and need the total for 5 cartons. the expression is 3 to 4 times 5. To solve this, think of the 5 as 5 over 1. We multiply the numerators. 3 times 5 is 15. The denominators are 4 times 1, which is 4. This gives us the improper fraction 15/4. To make this practical, we divide 15 by 4, which goes 3 times with 3 left over, resulting in 3 3/4 liters. Always convert your final answer to a mixed number for clarity in measurements. On slide 15, Bella exercises for 1 and 2 to 3 hours daily. We need the weekly total, which means multiplying by 7. First, let's master the conversion. 1 whole hour is 3 over 3, so 1 and 2 to 3 is 3 to 3 plus 2 to 3, which equals 5 over 3. Now, we multiply 5 to 3 by 7. 5 times 7 is 35, so we have 35 to 3. Dividing 35 by 3, we get 11 with a remainder of 2. Thus, Bella exercises for 11 and 2 to 3 hours a week. Breaking down the whole into its fractional equivalent is the safest way to convert mixed numbers. Slide 17 brings us to weights. We use 7/15 of a 360-gram bag of flour, while you could multiply 360 by 7 first. That leads to a very large number. Instead, use the principle of cross reduction. We ask, how many times does 15 go into 360? By dividing 360 by 15, we find it is exactly 24. Now, our problem simplifies significantly to just 24 times 7. This equals 168 grams. Cross reduction is your best tool for keeping numbers manageable and preventing large-scale calculation errors. Example 5 on slide 18 introduces comparative quantities. Bella has 14 yellow sheets, and her red sheets are 1 and 1.2 times that amount. This is a ratio problem. Look at the bar model. It shows the red quantity is the original 14 plus an extra half of 14. This visual analysis tells us immediately that the answer should be 14 plus 7, which is 21. Before calculating, always use the diagram to estimate your answer. This acts as a logical check for your final numerical result. Let's execute the calculation for slide 19. We have 14 times 1 and 1, 2. We convert 1 and 1, 2 to 3, 2. Now set up the expression 14 times 3 over 2. We can reduce the 14 and the 2. 14 divided by 2 is 7. Now we are simply left with 7 times 3, which is 21. By converting to an improper fraction and reducing before multiplying, we turn a mixed number problem into a simple single-digit multiplication. This systematic approach ensures 100% accuracy every time. Slide 22 returns to the bakery. 30 pineapple buns and raisin buns are 1 and 1 to 6 times that quantity. Converting 1 and 1 to 6, we get 7 to 6. Set up your expression 30 times 7 to 6. Notice that 30 is a multiple of 6. By dividing 30 by 6, we get 5. Now 5 times 7 gives us 35 raisin buns. Whether you're counting buns or sheets of paper, the logic of the mixed multiplier remains constant. Convert, reduce, then multiply. Master this rhythm and you'll master fraction multiplication. Next, slide 23, comparing a 3 and 3/5 meter bamboo stick to a 7 to 9 length iron bar. This is a multiplication of a mixed number and a proper fraction. First, convert 3 and 3 to 5. 3 wholes is 15 to 5, plus 3 to 5 gives us 18 to 5. Now, multiply 18 to 5 by 7 to 9. Look for the cross reduction, 18 and 9. 18 divided by 9 is 2. Now multiply across. 2 times 7 is 14 in the numerator, and 5 times 1 is 5 in the denominator. 14 to 5 simplifies to 2 and 4 to 5 meters. Every step counts. Finally, slide 24. Converting fractional hours to minutes. Jenna practiced for 7/12 of an hour. To solve this, we must use the constant conversion factor. 1 hour equals 60 minutes. We multiply 60 by 7/12. Again, we use reduction first. 60 divided by 12 is exactly 5. Then, 5 times 7 equals 35 minutes. By anchoring your fractional calculations to known constants, like 60 minutes, you can solve any unit conversion problem with ease. Great work today. We've mastered some tough concepts. Stay tuned for the remade Video 3. Welcome to the remake of Video 3. We are tackling advanced multi-step problems. On slide 25, we have 30 students in a class. The problem states that 1/6 of them take part in the long jump. This is our base quantity. Conceptually, you are partitioning the entire class into 6 equal groups and focusing on just one. This step is vital because the rest of the problem depends on finding this specific number correctly. Always identify your starting population before moving to comparison steps. Slide 26 introduces the second layer. The running race participants are 1 and 4/5 times the long jumpers. It's critical to realize we are no longer using the class size of 30 as our multiplier. Instead, we are using the result from the long jump. The bar model illustrates this dependency. The running race block is scaled relative to the long jump block, not the whole class. Understanding which quantity is the reference is the difference between solving the problem correctly and making a common logic error. On slide 27, we combine these steps into a single mathematical chain. 30 times 1 to 6 times 1 and 4 to our 5. First, convert 1 and 4 to our 5 to 9 to our 5. Now, look for global reduction. 30 divided by 6 is 5. That 5 in the numerator then perfectly cancels out with the 5 in the denominator of our second fraction. We are left with just 9. By chaining the expressions, you can see how the entire class population filters through the fractional requirements to give you the final count of 9 students. Efficiency through chaining is a pro-level math skill. Slide 28 presents a nested ribbon problem. We start with 7 to 8 meters of red ribbon. The green ribbon is 6.7 of that length. This is a fraction of a fraction. The bar model helps us visualize that the green ribbon is a slightly smaller portion of the original length. Before you calculate, ask yourself, should the answer be more or less than the original? Since 6/7 is less than 1, the green ribbon must be shorter. This logical check ensures your final answer is anchored in physical reality. Now, slide 29 adds the final layer. Haley uses 2/3 of that green ribbon. We now have a 3-part chain. 2/3 of 6/7 of 7/8. Each of is a multiplication sign. The diagram shows us narrowing our focus from the red ribbon to the green ribbon, and finally to the specific portion used for wrapping. In multi-step problems, don't calculate the middle steps. Write them all out in a sequence so you can look for massive simplification in the next step. Look at the solution on slide 30. We have 7/8 times 6 to 7 times 2 to 3. The 7s cancel out to 1s immediately. The 6 and 3 reduce to 2 and 1. Now we have 2 times 2 in the numerator, which is 4. That 4 reduces with the 8 in the denominator to give us exactly 1 to 2. In just seconds, our complex 3-layer problem is simplified to half a meter. This proves why you should never multiply large numbers first. Cross-cancellation does the hard work for you, leaving you with simple, manageable numbers. Slide 31 covers unit conversion within fractions. We have 325 of a liter of fish sauce and need the volume in milliliters. The principle is to multiply the fraction by the conversion constant, 1000. Set up 325 times 1000. Use your division skills. 1000 divided by 25 is exactly 40. Now, 3 times 40 equals 120 milliliters. By mastering the common conversion constants, like 1000 for liters, you can seamlessly move between different scales of measurement using fraction multiplication. Slide 32 is an inventory challenge with 120 cartons. 1 and 8 are lemon tea, and soy milk is 1 and 2 to 3 times that number. This sequential logic is the hallmark of advanced word problems. Convert 1 and 2 to 3 to 5 to 3 and chain it. 120 times 1 to 8 times 5 to 3. First, 1 to 20 divided by 8 is 15. Then, 15 divided by 3 is 5. Finally, 5 times 5 gives us 25 cartons of soy milk. Breaking the chain into these small division then multiplication steps makes even the largest inventory problems easy to manage. Our final deep dive for video 3 is slide 33, a complex costing problem. We multiply the unit price of $47.12 by the fractional weight and the comparison factor. This requires 3 conversions to improper fractions and a systematic reduction process. By focusing on each fraction individually and then looking for common factors across the denominators, we arrive at the precise total of $17.10. Accuracy in multi-step problems comes from patience and systematic work. Excellent progress! Remade Video 4 is coming up next. Welcome to Video 4. We start with Exercise 13, Problem 1. Jordan runs 4 rounds of a 2 par 5 kilometer track. This is a classic case of multiplying a fraction by a discrete whole number quantity. The expression is 2.5 times 4. When we calculate this, we get 8.5, which we convert into the mixed number 1 and 3.5 kilometers. Notice that the denominator remains 5 because the size of one round doesn't change, only the number of rounds does. Always verify that your distance makes sense. 4 rounds of nearly half a kilometer should be nearly 2 kilometers. Problem 2 involves scaling a physical material, a 180 centimeter ribbon where we use 7/15 of it. Here, we apply the divide by the bottom, multiply by the top strategy. 180 divided by 15 is 12. Then, 12 times 7 gives us 84 centimeters. In problems like this, always be mindful of your units. We started with centimeters and we end with centimeters. This technique of using the denominator as a divisor is the most efficient way to handle large whole numbers when finding a fractional part. Problem 5 asks for the length of a movie in minutes, given it is 1 and 11:15 hours long. This combines unit conversion with mixed number multiplication. We know 1 hour is 60 minutes. First, convert 1 and 11:15 to 26:15. Now multiply by 60. By reducing 60 and 15, we get a factor of 4. Finally, 26 times 4 gives us 104 minutes. This problem highlights why improper fractions are so valuable. They allow you to treat the whole and the part as a single unified quantity during the calculation. Problem 7 is a sophisticated multi-step costing problem. We have the cost of chicken wings and then use a scaling factor of 1 and 5 to 12 to find the steak cost. Finally, we need the total for a specific weight. This requires a chained expression, the unit price times the scaling factor times the final weight. By systematically converting each mixed number and looking for reduction across the entire chain, we arrive at the total cost of $90 and $310. In multi-step problems, the most important step is setting up your chain correctly before you start calculating. Let's review the fundamental summary of our module. When multiplying a fraction by a whole number, the core rule is to multiply the numerator by the whole number while leaving the denominator unchanged. This slide illustrates 5 6 times 7. 5 times 7 is 35, giving us 35/6 or 5 and 5/6. Conceptually, remember why this works. The denominator represents the identity or size of the parts, which stays the same. You are simply increasing the count of those parts. When dealing with mixed numbers, the golden rule is consistency. Always convert to an improper fraction first. As shown here with 1 and 110 times 15, we convert to 1110 before multiplying. This ensures that the whole number and the fraction are treated as a single quantity. Then, we look for reduction. Here, 10 and 15 reduce to 2 and 3 using their common factor of 5. This leaves us with 33/2, or 16 and 1 to 2. Never skip the conversion step. It is your safeguard against calculation errors. What if we have 3 numbers? The principle remains the same. Any numerator can be reduced with any denominator. Look at this example. 710 times 3 8 times 5 6. We can reduce the 5 and 10 to 1 and 2, and the 3 and 6 to 1 and 2. This leaves us with 7 times 1 times 1 over 2 times 8 times 2. The result is 732. By reducing everything first, we avoided having to multiply large numbers like 10, 8, and 6. Reduction is your most powerful tool for simplifying complex expressions. Our final technique summary involves a triple product with a mixed number. We convert the mixed number 2 and 4 5 into 14/5. Now we have a chain of 3 fractions. Look at the cancellation. The 5s cancel out, the 7 and 14 reduce to 1 and 2, and the 2 and 8 reduce to 1 and 4. We are left with 3 and a 4. This is the master algorithm. Convert all numbers to fraction form, reduce everything possible, then multiply across. This single method handles every problem in this entire module. As we wrap up our summary, remember this expert advice. When solving problems, analyze the information in the question carefully before writing the expression for calculation. Don't rush into the math. Ask yourself, what is the whole? What is the portion? What are the units? Once your expression is correctly structured, the calculation becomes a simple mechanical process. Follow this approach and you'll solve every word problem with confidence. In our final video, we'll tackle the integrated Christmas challenges. Welcome to our final video in the series. We conclude with the Celebrating Christmas integrated exercise. In problem 1, Mom is preparing 1 7/8 liters of punch, and 3/5 of it is juice. First, we must calculate the exact juice requirement by multiplying these two numbers. But the challenge doesn't stop there. We then have to compare this requirement to the 1 3/10 liters currently in the refrigerator. This problem teaches you sufficiency analysis. First, find the needed amount, then compare it to the available amount. It's a critical skill for real-world budgeting and planning. Problem 4 introduces a logistical constraint. Only one plate of food fits in the oven at a time. It takes 1 4-hour to bake one tray, and we have 3 and 1 to 2 trays. This is a classic rounding up logic problem. Since you can't bake half a tray separately in half the time without still using the oven, you must realize that 3 and 1 2 trays actually requires 4 separate baking sessions. We then multiply the 4 sessions by 1 4-hour per session to get exactly 1 hour. This slide is a masterclass in reading the fine print. Always note the physical constraints described in the problem before starting your math. In problem 5b, we see a comparative weight challenge. A mango weighs 3/8 of a dragon fruit. Looking at the scale, we see the dragon fruit weighs 2.5 of a kilogram. Our expression becomes 3.8 times 2.5. This is where your reduction skills shine. We can reduce the 8 and 2 to 4 and 1. Multiplying across gives us 320 of a kilogram. Visualizing these fractional weights on a scale helps bridge the gap between abstract numbers and physical mass. Always check. Does 320 look like it should be smaller than 2.5? Yes, it does, confirming our logic is sound. Problem 6 is a high-level 2-part problem. Dad buys 15 and 3 to 4 meters of ribbon at $8 and $2 to $5 per meter. Part A asks for the total paid, a multiplication of two mixed numbers. Part B, however, asks for the amount used to decorate, which is 8/9 of the total length purchased. This slide tests your ability to distinguish between cost and quantity. To solve Part B, we multiply the total length, 15 and 3 per 4, by the usage fraction, 8/9. Converting to improper fractions and reducing systematically reveals that Dad used exactly 14 meters. Precision in identifying which numbers to multiply for each sub-question is key. Mathematics isn't just about numbers. It's also about spatial relationships and directions. In problem 7, we must locate the Christmas tree relative to the sofa using given compass directions. If the dining table is to the west of the sofa, we establish our orientation. By analyzing the grid layout, we find the tree sits in the southeast position. This spatial reasoning problem demonstrates that the logic used to divide fractions is the same logic used to divide space. Clarity in establishing your reference point, the sofa, is the first step to a correct solution. Problem 9 brings us to the store for some Christmas card shopping. We have 2 different products with 2 different unit prices. This is a multi-step addition and multiplication problem. We need 8 cards of type A at $4 each and 6 cards of type B at $5 each. We calculate the subtotals. 8 times 4 is 32, and 6 times 5 is 30. Summing these together, we find the total is $62. This problem simulates real-world budgeting where multiple rate times quantity calculations must be performed and aggregated. It's the ultimate practical application of the scaling principles we've mastered. Our final challenge is problem 10, a geometry synthesis problem. Bella overlaps 2 identical triangles. To find the area of the resulting composite shape, we must first understand the area of a single triangle. 1 2 times base times height. Each triangle has a base of 8 centimeters and a height of 8 centimeters, giving an area of 32 square centimeters. However, when overlapped, they share a 4 centimeters base region. We must calculate the area of the overlap and subtract it from the sum of the 2 triangles, or add the non-overlapping parts. This problem represents the peak of the module, requiring you to apply fractional scaling to geometric properties. Congratulations on completing this comprehensive deep dive.